Great. So, hi everyone. Welcome to my thesis defense. My name is Will Creighton. I'm a 6th-year PhD student here at Stanford, and this is work done under my advisors, Pat Henderhan, and my co-advisor, Manish Agrawala. So at a high level, my research is about combining cognitive psychology and programming language theory to make programming easier. And this is because programming has two fundamental components, a person and a program. And so cognitive psychology shows us how people work, meaning how they see the world, how they form memories, solve problems. And PL theory shows us how programs and programming languages work, like their semantics, what they can compute, how expressive a given feature is, and so on. And my bet as a researcher is that if we can put these fields together, we'll be able to design better tools for programmers. And concretely, I follow this methodology for bridging the two fields. First, I seek to identify how cognitive limitations make a given programming task difficult. So, no worries. So, when it's the challenges of an in-person event. All right. So when we look at a program, when we read it, when we debug it, when we try and remember things about it, can we use principles of cognition? There's still some chairs there if you want to sit there or in the back. Can we use principles of cognition to predict when people will struggle with those tasks? And second, I apply PL theory to design a system for overcoming these limitations. So here, the role of PL theory is to avoid building ad hoc solutions and rather to build a system that is provably correct and generalizes to as many programs as possible. And finally, I demonstrate that system can help programmers actually complete their task, which is important because cognitive psychology is often low level, looking at very specific phenomena, whereas programming happens at a longer time scale. And so this step helps bridge that gap. Okay, so overall, this is my approach. And my thesis represents one instantiation of this methodology, which you can see kind of like a Mad Lib, filling in the blanks. So in this thesis, I started by focusing on working memory, how that makes a simple task called program tracing difficult, which led me to think about reducing working memory load by reducing the amount of code that programmers have to read or reducing code context. And the mechanism for that was information flow analysis, which was enabled by ownership types. And then finally, I turned that into a program slicer and showed that it can help programmers find relevant code while debugging. Packing that all into one sentence, my thesis is that ownership types enable the modular static analysis of a program's information flow, which programmers can use as program slices to find code relevant to their task. Okay, that's a ton of concepts and a ton of jargon, so I'm going to unpack it step by step, and hopefully this will all make more sense by the end of the talk. So step one is to identify cognitive limitations that make a given programming task difficult. So this is where the research began about 2 years ago. And the specific aspect we decided to investigate was something called working memory, or how programmers can struggle to remember information about a program. Now, to build some intuition for this idea, I want to start by talking about a program that all of us have experience dealing with, and that is a recipe. So I'm going to tell you the story of when I made lemon meringue pie for the first time and how easy it is to forget very important things in the process. So to make this pie, I Googled for a lemon meringue pie recipe. I found a good one and gathered up all the ingredients on my countertop. And then my wife reminds me, Marianne says, only put in half the sugar. I don't want this pie too sweet. And I say, yes, dear, I got it. So I take a look at the directions on my phone. I prep the ingredients. I'm squeezing and zesting the lemons. Now I'm ready to make the filling. But like all of these recipes, it just says, okay, put in big list of things. And I'm like, wait, okay, how much water? So I go scroll up. All right, 1.25 cups. And then what was the thing? Sugar. How much sugar? 1 cup of sugar. Cornstarch. And then I go back and forth 100 times until finally it's all in the pot, at which point, put it on the stovetop, boil it down. And unfortunately, I turn around and, oh my God, my cat's on the table. I got to get him off before the health inspector sees. So I get him down. And then I'm like, wait, what was I doing? Oh, I think I was blending the egg whites for the meringue. And then my wife says, hey, didn't you skip a step? And I'm like, oh God, I forgot to put in the freaking egg yolks. So I grab the egg yolks, I mix them in, but this part's a little bit tricky and I kind of forgot how to do it. So now I'm looking around for my phone and I forgot where my phone is. So I'm running around trying to find that. It was under a paper towel. So I got my phone, I read the directions, finally mixed together the meringue, put the pie in the oven, and it comes out quite nicely, I think. So we chill it overnight. We're ready for that amazing piece of pie the next morning. Marianne goes in for the first bite and she says, "It's okay, but it's a little sweet." I'm like, "No, I forgot to have the sugar." Oh, yeah. So another day. But the point of this example is that you can see how at every turn, the biggest challenge I faced was following the recipe with my memory, that I kept forgetting a quantity, a step, a state, or just some other aspect of this process. And drawing the analogy to programming, you can view a recipe like a program. It has well-defined steps, dependencies, variables, and so on. And so just like following a recipe is challenging for your memory, so is following a program. That forgetting how much sugar you're supposed to put in is like forgetting the value of a variable on a particular line of code. And this intuition is well supported within cognitive psychology. That the relevant aspect of cognition is what's called working memory. So the basic idea is that you receive some information, right? Marianne says, only put in half the sugar. And that goes from my ear into my working memory, the auditory store specifically, where my brain stores that information in the short term. Then that information either gets cognitively processed or stored in long-term memory, or most likely it's just forgotten. And a key result from cognitive psychology is that everyone, like you and me and everyone in this room, we have very limited working memories, that you can't remember more than 7-ish arbitrary things at a time. And this result has deep implications for all kinds of tasks, whether it's playing chess, driving a car, reading a data visualization, but there hadn't been as much work connecting this to programming. And so our first goal was to explore, how do working memory limitations influence a person's ability to read a program? And we ran a number of experiments here, and I'll describe one that captures the key ideas. So the guiding question of this experiment was, what is the precise set of mental steps that a person would go through while tracing a program? And by tracing, I mean, just tell me what the value of Q is on the last line here. Like no higher level comprehension, following the mechanics, just like following the mechanics of a recipe. And to keep it simple, we started with programs that just use variables and arithmetic. Our hypothesized cognitive process is that first you would store x associated to 3 in your working memory, then compute x plus 4 by looking up the value of x in memory, computing 3 plus 4 in your head, storing y goes to 7, and so on. And one way to view this model is by thinking about a person's attention over time. So this graph shows each line of code on the y-axis and then time on the x-axis. So if you read the first line of code, second and third, you would see a line like this. But then let's say you forgot the value of y while reading that line. Then you would go back to the definition of y to remember what it was, and then continue tracing the program. And so the idea is that revisiting a piece of code you've already seen is an indication of working memory failure. And our basic hypothesis is that for a sufficiently large program, we should see evidence of working memory limitations when people frequently revisit code. So to test that hypothesis, we asked participants to trace short programs using this web UI. Each program was 7 lines long, had the same structure of assigning variables and numbers to expressions. And then to track participants' attention, we blurred out the right-hand side of each assignment. And then we unblurred the text when the user hovers over the line with their mouse. So that way the mouse is like a proxy for their attention, sort of like an eye tracking study that we could run remotely during COVID. And we did 150 trials over 15 participants. And to give you a sense of the data, here is one trial from a participant. So you can see how they visited the first couple of variables, they hit this expression, and then they immediately forgot the value of y, so they go back and visit it again. And so the first thing we did is count the number of times a participant revisited code per trial. And what we find is that even with 7 lines of code, on average, participants revisited code 11 times, with the distribution ranging from 0 to as many as 40. And I think this is kind of striking in of itself. Like, this is the simplest possible program and the simplest task you can imagine. And participants still forget everything when we ask them to trace. And the story gets even more interesting when you look closer at the data, because we realized that participants would use one of two distinct strategies. So in the top row are examples of what we called a linear strategy, which is the original model I proposed, that participants trace top to bottom and go back to observe code that they forgot. But in the bottom row, we saw participants use what we called an on-demand strategy, where they started at the value they needed to compute and then traced by following the data dependencies. So in the bottom left here, if they saw B is O plus S, they went from O to here and S to here and so on. And this distinction is interesting because it leads us to a deeper consideration of how working memory is being used in each case. So in linear tracing, the thing that you're holding in your head are these pairs of variables and values, like H is 3, J is 4. But when you forget them, you have to go look up the definition. But if you're tracing on demand, the working memory load is totally different. You don't need to remember all these variables because you're just looking them up. And instead, you have to remember program locations. So if you jump from B to S to Y, you have to remember to go back to S when you're done. And if you don't, you have to visually search for that location to figure out where you came from. And so the takeaways here are that first, working memory severely limits programmers from remembering program state while tracing. And second, that programmers will use different tracing strategies that affect the nature of working memory usage. And so these are psychological observations, like realities of cognition. But as a computer scientist, I also care about design. How can we build tools that help programmers deal with the reality of their forgetfulness? One form of design is to use the programmer's editor to show information about a program. So for example, many theorem provers like Lean will have a panel that shows you the name and type of all variables in scope of your cursor. So this helps a user who's linearly reading through a program know what facts are true at a given point in a proof without needing to go back and read all that code. Another example is Dr. Racket, where if you hover over a variable, then you'll get these arrows pointing to all the locations in the program where that variable is used. So if a user is reading on demand, then this could remind them where they might have been looking before arriving at a particular variable. And in cognitive terms, we would say these are both instances of cognitive support, that these tools externalize information about a program into your editor. And if that interface is properly designed, then a visual search through the interface is less cognitively difficult than figuring out that information for yourself. And so it was in that vein we started thinking, what are other kinds of cognitive support that an editor could provide a programmer to reduce their information overload? And one technique I found particularly interesting is called program slicing. So program slices are the subset of code that is relevant to a particular value. So for instance, in this Fortran program, this thing at the bottom is the slice of the variable z. It is just the lines of code that are needed to compute that value. And the concept, as the use of Fortran suggests, was developed in the early 80s by HCI pioneer Mark Weiser. And he made two contributions. First, he showed that slicing had origins in human cognition. That is, when asked to debug programs, participants were more likely to remember code from the slice of the bug than other lines of code. Hence the paper title, Programmers Use Slices When Debugging. And based on this idea, he then formalized the concept of program slicing as an analysis that can automatically find the subset of code that affects a particular value. And I think you can see why slicing is appealing, that a slice should reduce the amount of code you need to read in order to understand any one variable. And so it should reduce the overall working memory load of program comprehension. And so when I was first researching slicing, I thought this is perfect. Like, let's grab a program slicer off the shelf and see if it can help people in practice. But I noticed something a little bit weird, that I couldn't find any program slicers. There are hundreds, if not thousands of papers that have been written about program slicing, but there were barely any practical tools that I could use today. And so I started investigating, how do you actually do program slicing? What makes it so difficult? And that leads me to the second step of my patented three-stage process, applying PL theory to design a system to overcome cognitive limitations. And here we change the task a bit from program tracing, which is a little too low level, to reducing code context, which is more what the goal of slicing is. And instead of tackling this directly as a slicing problem, we use what's called information flow analysis based on the mechanism of ownership types, which are both new concepts. So I'll start with information flow. All right, so we say that a variable x has an information flow to y if x can influence the value of y, or that x can cause a change in the value of y, or that y depends on x. There are many ways you can think about this. And there's a more formal definition, but I'm going to stick to plain English for this talk. So to illustrate this idea, here is a C++ function. I sincerely apologize for bringing C++ into your life, but it's important for this talk. So we're going to use this as a running example. I encourage you to actually read the code and make sure you can follow along. This function copies all of the elements from one vector v to another vector v2 up until some index max. And it does that by initializing I to 0, creating an iterator x over v, which then for each x says if I is max, break out of the for loop. Otherwise, add x to v2 and then increment I, and ultimately return v2. So in this function, we can say both v and max have an information flow to v2. They both influence its value, and they do it in different ways. So first, there is an explicit flow from v to x to v2, where here v goes into this operation, which goes into the iterator, which goes into this dereference, which goes into this operation, which affects v2. This is more, you would also call this a data flow. So that's why that v influences v2. But there's also an implicit flow from max to v2. So here, this break statement determines how many times we run pushback. And so even though the value of max is not directly used to change v2, its control flow influences the ultimate value of v2, and therefore we would say both of these instances are information flow. It is a term meant to capture both of these kinds of influence. And this definition is useful because it shows us that program slicing is a special case of information flow. That a backwards program slice of x is the set of code that has an information flow to x, like the set of code that can influence its value. And then a forward slice is the code with a flow from x, meaning x affects that code. And so if we have an information flow analysis, then we have a program slicer. And this is a useful shift in framing because there hasn't been as much recent research about slicing, but there's been a lot of research about information flow. So specifically in the last 2 decades, researchers have made many languages and frameworks for doing what's called information flow control, or preventing leaks of sensitive data. So there's FlowCamel, which extended OCaml, and JFlow, which extended Java, and several systems for native Haskell. And these are all fantastic research efforts, but they suffer from a big problem, which is most people don't use them. Like part of the reason is that to use these tools, you have to structure your program around the tool. Like you have to add all of these annotations, or God forbid, you have to use Haskell. And for us, we wanted an information flow analysis that would seamlessly integrate into your existing code base. Like you can just drop it in and it'll work within seconds, regardless of what kind of domain you're working on. And so to understand why that's challenging, let's imagine how you would implement an information flow analysis for the C++ program that we just saw. So recall that this function copies the elements 0 to max into a new vector. And there was an information flow from v to v2. So if you had to specify an algorithm for determining that fact that we intuitively identified, how would that algorithm work? And it would need to deduce a few key facts. The first is that when we do x parentheses v dot begin here, this creates an iterator, which is a pointer to v. We need to know that x points to v, and specifically, and not whatever other data. So that way, when we see x being used here, we know that v is involved. This is the pointer problem of knowing what X points to. And the second thing we need to know is that when we call pushback, that actually mutates V2 with X as input, and that establishes our information flow. This is the mutation problem of knowing what this function call will change. Okay, and so just brainstorming, what are some ways we could address these problems in an algorithm? Well, one possibility is just define it away. Our analysis only works on programs that don't use pointers and don't use mutation. But that's how most of the world works. Everyone uses those two things, so not a great answer. We could have the user write down somewhere, like the pointer returned by this function points to data within the vector, or pushback mutates its input. But that's asking the user to do work for the tool. That's a no-go. We want a zero configuration solution. We could run the program and look at the execution and see that X points to V, or that V2 is mutated. But what if your code runs on a satellite or submarine? I mean, dynamic analysis just gets arbitrarily hard in some code bases. So we would prefer a static solution. Meaning the last option available is to look at the source code of the dependencies, to look at the definitions of begin and pushback. And so we could see in the source a pointer being created or a vector being mutated. But even this is not always practical. Libraries may only ship type signatures and not actually source code. We would prefer a more modular solution. And so another way to think about this is to rephrase these discarded solutions into design criteria. That is, we want an information flow analysis that works with realistic features, that has no added configuration, that does not require executing the program, and that does not require access to the source of dependencies. So if we can't do this for C++, then what other language features are required to make this possible? And one angle on this question is to ask, what are other kinds of program analyses that are also subject to all four of these constraints? And it turns out that one answer is memory safety. So to explain, let's modify this program to not just copy elements, but remove them from the input vector. So we'll call it drain till. And the only change is this line, v.erase x. So the last program, totally fine. This program should make you sweat. If you run it with the right input, you will get a seg fault. And this is because the code that iterates over the vector does not play well with the erasure, that it can move elements around in the array, leading the iterator to point to invalid memory. And more generally, memory unsafety arises under two conditions: that you have multiple aliases of the same object, and that you mutate the object through one of those aliases. And so that means any tool that checks a program for memory safety has to understand aliasing, or pointers, and it has to understand mutation, which were our two problems. And there just so happens to be a language dedicated to protecting memory safety. I hear every grad student groaning in the background from years of listening to me, and that's Rust. So here's the same C++ program, but written in Rust. It should look similar. It has roughly the same structure. It says, make a vector v2, iterate over v with this iter method, and then use enumerate to get the index I. If I is max, we break. Otherwise, we push x into v2, and then remove the first element from v. So this program has the same bug. It would seg fault if we ran it. But the difference is when I ask the Rust compiler to run this program, I get an error from what's called the borrow checker. And it says this: cannot borrow v as mutable because it is also borrowed as immutable. And it correctly observes that v.iter creates a pointer to v. That's the pointer problem. And that v.remove tries to mutate v. That's the mutation problem. And the combination of these is memory unsafe. But in order to bring this back to information flow, we first need to unpack how exactly Rust finds this error, or how the borrow checker works. And here we now arrive at the concept of ownership types. So ownership is a bundle of related concepts about changing the type system to track who has access to what data at what time. And to see that in action, I changed our drain2 program in two ways. First, I expanded some syntactic sugar, so there's no method calls, just function calls. And whenever we see a reference, it has now these curly braces with annotations. And then I also grayed out the code that's not relevant to the slide, the slide slice, if you will. And the key idea for ownership types is that every pointer type in this program is annotated with two things. The first is a lifetime, written as tick a character, that indicates how long the pointer will live. And the second is a mutability modifier, that either mute or no mute, that indicates whether the data under the reference can be mutated. Now, it's worth noting here that unlike C++, the no mute modifier is transitive. So nothing accessible through a no mute reference can be mutated, which is not true of const in C++. And also note here that this syntax is totally made up. Like the curly braces and the no mute don't exist in Rust. They're just here for clarity. All right, so with these two annotations, now we can see how the compiler identifies the memory safety bug. The first thing the compiler does is it associates each lifetime with an actual range of code for which the reference is live. That looks like this. So here, the lifetime tick D is only used on line 8. The lifetimes tick C and tick B are used throughout the for loop. And the lifetime tick A is used in the entire function. So the important part of this step is to understand how the compiler knows that the lifetime tick B should last from lines 3 to 9. Because we create this reference and tick B to V, and we pass it into vec_iter. There's nothing obvious in this program that says tick B should last beyond line 4. But the reason we know that tick B and tick C have the same lifetime is because of the type signature of the iter method. It specifically says that this takes as input a no mute reference to the vector with lifetime tick A, and then it returns an iterator which produces items of type reference to T, also with lifetime tick A. So the type signature uses this lifetime parameter to relate the input and output pointers. Because they share a lifetime, and we know that tick C must last for the for loop, that tick B must also last for the for loop, using just the type. And so this is the first step. Then the second step is to identify conflicts. So we can see that tick B points to V with a no mute modifier, and that tick D points to V with a mute modifier. And the reason why tick D is a mute pointer is because the type signature of the remove function says that it must be. The only way to remove from a vector is to get a mutable reference to it. And so from the first step, we know that tick D and tick B are live at the same time. And that means the difference in mutability modifiers identifies the memory safety violation, that you are not allowed to remove from the vector for the duration of the lifetime tick B. Okay, obviously that's a lot of details, but this is the technical meat. These are ownership types. This is how they enable the borrow checker to find memory safety violations. And importantly, this analysis is mostly practical by our standards. It works with pointers and mutation. It doesn't require executing the program. And it only uses type signatures to analyze dependencies. It's modular. But it requires users to add annotations to programs. So people have to go in and they have to add these tick A's and mutes and stuff everywhere they're using their Rust code. But it turns out people are willing to do that in exchange for memory safety. And so these annotations exist in every Rust program. All we have to do is repurpose them for information flow. And so returning to the copy to example, but written in Rust, remember that the challenge was determining that there's an information flow from V to V2. We had to know the pointer problem that X points to V and the mutation problem that push mutates V2. And we solved both of these problems using ownership types. So first, we know that X points to V because X shares a lifetime with V. And the generalized version of this is that for any pointer P, its points to set can be determined solely from the lifetime of the type of that pointer, which I haven't described the exact construction of that set, but hopefully you get the fuzzy idea on the previous slide. And then for the mutability problem, we know that vec push mutates v2 because it takes a mutable reference as input. And the general rule is that if you call a function with some arguments, we'll say that all of the inputs have an information flow to mutable pointers inside of the argument. And conversely, if we have an input that is under an immutable pointer, we know it cannot be changed, and therefore it has no added flows when we call the function. Okay, so these are really the core rules that form the theoretical basis of our information flow analysis, plus a bunch of other ones I haven't shown but aren't nearly as interesting. So to evaluate this theory, we wanted to understand two questions. Is it sound and is it precise? So by soundness, I mean that if an information flow exists in the program, our analysis will find that information flow. And we made a formal proof of soundness with a couple of tricks. This is mostly for the PL heads in the room, so if it's too much Greek, don't worry. First, we leveraged some work called Oxide that formalizes the semantics of safe rust. And then we embedded what's called a dependency calculus into the Oxide type system. So this judgment here shows the base Oxide typing judgment in black with our added dependency calculus in red. And then we extended all of the Oxide inference rules to compute dependencies. And so finally, we could write a theorem that precisely describes the conditions under which our analysis is sound, namely non-interference, which is a common technique in the security literature. And there's a big proof of this in the PLDI paper, but the high-level idea is that we used a theoretical foundation to prove the soundness of our analysis. However, although this analysis is sound, it is sometimes imprecise. So by that, I mean our tool will say two things have an information flow when they do not. And this is a consequence of our rules being approximations. Just as one example, in this program, we create a vector v and then a mutable pointer x to an element of v, but then we don't mutate x. So line 2 has no effect on the vector v. But the getMut function down here takes as input a mutable pointer to the vector. And so our analysis says, because it takes a mutable pointer, if we don't look at its definition, we have to assume that calling v.getMut could change v, even though the only reason it's taking this mutable pointer is to sort of pass that permission off to the element of the vector. And therefore, our analysis is imprecise in this case. We would say this line is relevant to v when it is not. There's a mismatch between our assumptions and reality. So we have to understand an empirical question. How often do programmers write code fitting these kinds of patterns? And we investigated this question in 3 steps. So first, we created a whole program variant of our analysis. So basically, whenever it sees a function call, rather than just inspecting the function's type signature, it will recursively analyze information flow if the function source is available. And this is a lot slower, but it's more precise. So it would recognize, for instance, that getMut does not mutate v. Then we took these 2 analyses, the modular and whole program one, and we ran them on every variable in every function in 400,000 lines of code from popular Rust code bases. And so for any variable, we could then compare the information flow computed by one analysis versus another. And the key finding is that in 94% of cases, they are exactly the same. That is, the whole program analysis was not more precise generally than the modular one. And a way to interpret that is with ownership types, you don't lose much information by only looking at the type signature. Like if a function says it's going to take a mutable pointer, it's probably going to mutate that object. And so all in all, what we showed is that first, ownership types can be repurposed to modularly analyze information flow involving pointers and mutation. And second, that the modular approximation is provably sound and empirically precise. All right, so armed with these facts, we finally set out to finish what we started, and that was build a program slicer. Let me show you what that actually looks like. So let's get this up on the screen. Let's reshare new share so our remote friends can see it too. Okay. So if you open a Rust workspace in Visual Studio Code, I'll bump up the font size a little bit, you can enter the slicer like this. And now what will be visualized is the forward and backward slice of whatever variable or expression you've selected. So the slice is visualized by fading out code that is outside the slice, and then also by highlighting in light gray any direct mutations or references to the tool. The tool instantly responds to a change in focus. So as you click through to different parts of the program, then you'll get to see the forward and backward slice of whatever you've selected. And this tool is the culmination of the technical parts of my thesis. It's publicly available, it's open source. If you go to the extensions tab in VS Code, just to show you, type Flowistry, the name of the system, then you can see it right there and download it yourself if you are interested. And Rust developers seem pretty excited about the tool. We've had over 1,000 downloads in the extension marketplace, gotten over 1,000 stars on GitHub, so people want to use it. The crowds are calling. But before we get too excited, with this system developed, we still needed to finish with our step 3 of checking if this tool actually serves its intended purpose. So let's bring that back and once again share the other screen. All right. And so what we wanted to do is demonstrate that the program slicer can actually help programmers, in this case, find relevant code while debugging a program, was the task that we selected. And the basis of this study was the idea promoted in pretty much every paper on slicing since its inception, which is the relationship between slices and relevance. So you'll see a lot of quotes in papers like this. Slicing is the idea of ignoring irrelevant code, that a slice is constructed by deleting the parts of the program that are irrelevant to the values stored in the chosen set of variables, right? These are how people define and think about slicing. Of course, when these researchers say relevant, they really mean information flow. Like if code cannot affect the value of this variable, then it is irrelevant. But I think there's also a human-centered definition of relevance, which is if me seeing the code influences my human ability to understand it or fix it, it's cognitively relevant. And so the goal of this study was to examine the relationship between relevance as a formal construct, like the information flow definition, and relevance as a cognitive phenomenon. Because the closer these two are to the same, the more we would expect a program slicer to help programmers find relevant code. And so to answer that question, we designed an experiment where we recruited 18 Rust programmers and asked them to debug a series of relatively short Rust programs that we designed. Each had a bug represented by a failing unit test, and they were all designed to have more code than was relevant to the bug. So finding the relevant code was part of the task. We had participants debug 2 of these tasks with Flowistry and 1 without. And so we could compare for different programmers how they attacked the same bug in both cases. Now, given the complexity of debugging and the variance in participants' background, we weren't really looking for specific measures like, people are going to take X% less time with Flowistry than without, and blah, 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 blah. We approached this more from what you would call in HCI a grounded theory methodology of observing carefully each debugging session to see what patterns arose in participants' behaviors, and then also comparing commonalities in themes from interviews that we did after the sessions. And basically what we found is that Flowistry was very effective at helping participants catch some bugs, but not all of them. And there's a lot to learn from both cases. So first, we'll focus on the successful case. So in the URL task, participants were given a function that decodes a URL structure from a string. Part of this structure is this path component that contains, if you have A/B/C, then you get ABC as the components. And when that URL contains a query string with a question mark, then this query processing code down here post-processes that. And what it does is it actually pops off the last element of this vector But then the bug is it forgets to put it back after it's done processing it and after it's split off the question mark. And so in this task, participants were able to effectively use flowistry to both ignore irrelevant code and draw attention to relevant code they might have otherwise missed. So for example, here's a representative quote from a participant. They would say, okay, let's have a look at path, because we know that's the thing that we've got wrong since they saw that in the unit test. Then they'll click this in flowistry, which will visualize the slice as shown here. And immediately they say, I'm a bit wary of these pops because we might be popping things and then not saving them anywhere. And so you can see how the backwards slice facilitates finding this hypothesis. That not shown above is a ton of code that's faded out as irrelevant to this computation that participants were less likely to look at. And second, it draws attention to the fact that path is actually mutated in this block. Like most participants initially thought this just used it and didn't change it. And in fact, we found that participants with flowistry figured out that there was a bug likely in this code about 3.5 minutes earlier than participants without. And the two participants who didn't even finish the task who weren't using flowistry, they never even looked at this code. They just assumed the bug couldn't be there. And so I think this is a pretty compelling example of how this slicing has a clear relationship to relevant code, both in distinguishing from the irrelevant and drawing attention to the things that are relevant but you might not expect. But conversely, not all tasks went so well. So in the median task, participants were given a program that takes a list of countries and computes the median population grouped by continent. And the bug in this task is that the denominator down here is incorrect. It should have been dividing by the number of countries at the median, but instead was dividing by the number of countries in the continent. And I think the way the slice could have helped is that if you click on the denominator, it's sort of suspicious that so little of this calculation is relevant. Whereas if you click on the numerator, much more of the calculation pops in and becomes relevant. And so possibly by seeing this disparity, you might be able to identify the bug or the lack of relevant code. In theory, but that didn't happen. Not a single participant actually was able to make that deduction. And some participants even explicitly unprompted called that out. They're like, well, yeah, I guess if I clicked in the right place, I should have noticed that median countries wasn't highlighted. But I didn't observe that while I was doing it. And it could be because I'm not used to flowistry. So it just doesn't register in my head that it isn't lit up. And so in a sense, this task highlights, I think, a very fundamental fact. Just because code is outside of a slice doesn't mean it's irrelevant. If your bug is referring to the wrong variable, then the right variable might be outside the slice. And so this is why I think talking about slices as relevant code is not great from the user's perspective, because really it's about information flow. Does this code affect the variable as written? And it's very important that programmers using a slicer understand this distinction to use it effectively. And so our main takeaways from this study were, first, there are clear cases where slicing can help programmers find code relevant to their task. But second, that slices can still exclude cognitively relevant code, suggesting a need for a more nuanced understanding of relevance in programming. All right, that's my last contribution. So zooming back to the thesis, hopefully all of this jargon makes a bit more sense. What I've shown is that ownership types enable the modular static analysis of a program's information flow, and programmers can use that as program slices to find code relevant to their task. And this was built up in 3 steps, starting with an analysis of working memory limitations, leading to an investigation of slicing techniques, and culminating in a user study of our open source slicing tool. But of course, my lasting legacy will be definitively showing how not to make a lemon meringue pie. So looking at the future, I think there is tons and tons of interesting directions to take this work. One is a better study of how a slicer can be useful at scale, like especially over a longer period of time in larger code bases. So for example, I've personally been using flowistry to help me understand the Rust compiler and contribute fixes to the code base, like this PR that was merged last week. Another direction is to explore the security aspects. Like, one thing that's cool about information flow is it's a very general construct. And so it can be used for more than just slicing. I've been prototyping an information flow control framework for Rust. Another direction is to invent totally new ways of using information flow beyond slicing and IFC. So I've been experimenting with whether you can use information flow to automatically decompose a program into smaller pieces, highlighted in these colors here, by identifying like which chunks of code are more related to others than some others. And so all of these, I think, are super exciting. If any of you like Rust or information flow, you should totally talk to me. I would be happy to work on any of these things with anybody in the audience. So reach out. But otherwise, that's all I have. I hope you enjoyed the talk, learned something interesting. But before I wrap up, I would like to quickly make some acknowledgements of all of the folks who have been involved in my PhD. So I've had a very winding PhD. I started working on research that is completely different from what I just presented. Fun fact, I have never published at the same conference twice. I went from SIGGRAPH to K2D to Chi to SIGC to PLDI, and we'll see what happens next. And so I am immensely grateful to all the faculty, students, friends, and family who supported me on this winding road as I figured out my place in the world of research. First, I have to talk about what's called the Hanrahan cinematic universe. So the timeline of events, okay, here, the timeline of events leading up to today are that in 2002, Manish graduates from Stanford advised by Pat. Then in 2011, Kayvon also graduates from Stanford advised by Pat. Kayvon moves to Carnegie Mellon, where in 2016, I graduate advised by Kayvon as my undergraduate advisor. Then I get to Stanford, where both Pat becomes my advisor, and then later, Manish after him. What? When I started working with Kayvon, I had no idea I was getting tangled in this like deep secretive web of advisement. But I am, of course, deeply grateful to Pat, Manish, and Kayvon for all of the advice and helping me becoming the researcher I am today. I also have to thank, of course, the rest of my thesis committee. Sean for chairing, and probably mine and every other HCI students committee. So we deeply appreciate your service. Alex is my third reader, which is a ton of work to actually go through the stuff I write down. And of course, there were labels. And of course, the most work is Sriram, who agreed to be my postdoc advisor. So he stuck with me for the next 2 years. Thank you, Sriram. I want to thank all the administrators like Jay, Helen, Yari, all the staff who helped get the space ready, who have made my PhD amazingly smooth over the years, and putting up with all the times I turned forms in late. A big thanks to everyone in Pat's group. Sitting in Gates 392, I have acquired half a degree in electrical engineering by listening to talks about hardware design. Shout out to Manish's group, who are all amazing people with such varied interests that have made my time at Stanford incredibly enjoyable. And more generally, shout out to everyone who sits in 3B. This has been the defining culture of my time at Stanford. It's been a blast getting to know everyone. This photo is from our most recent trip to Tahoe. And by the way, I want to point out, I think this was supposed to be the fun photo. Look who's having the most fun. That's me in the back. No one else is having nearly as much fun. So I'm expecting a lot more next time. Of course, a massive thank you to my family who's on Zoom for always being supportive, helping me make it to the PhD in the first place. I have to give a shout out to my cat, Nabang, whose emotional support was just really essential during the waning stages of my PhD, and is literally the cutest and most photogenic cat one could ask for. And finally, I have, of course, grateful to my wonderful wife, Marianne, for supporting me the entire way. This is one of the first blurry photos of us back when we met at CMU. Then we graduated together. We dated long distance for 3 years while Marianne did her MFA. So we did a bunch of travel. Then time passes. We eventually got married 3 years ago. And now we live together happily with our cat child. And I'm sure that Marianne is not too much pressure, but eagerly looking forward to me passing my defense so that I, the computer science major, can contribute more than the minimum wage to our family. All right, that's actually all. Thanks again, and I'll open the floor for questions.
Yay!
Is this good? Let's make sure. All right, so the way we're gonna, y'all can hear me on the owl? Let me bring up this videos. I'll just stop sharing.
Comments on the.
Oh, hold on, I think I need to make sure I see this. All right. All right, so I think the way we're gonna do this is we'll just kind of try and mediate any questions from the audience or from the Zoom. If you're on Zoom and you have a question, then maybe if you can either put it in the Zoom chat or you can use the raise hand feature so we know that you want to ask a question. To get us started, does anybody physically in person have a question? Hey, Ron.
I had a question about what you've learned about the level of proficiency that programmers need to have to take advantage of these types of analyses. Is this a tool for a beginning user, or is this a tool for a strong programmer to work more productively? Do you have any perspective on that?
Yeah, it's a good question. So that is one thing we considered in the study of the slicer is we asked people how long they've been using Rust and how long they had programming experience overall. And we did find that people who had like 3 or fewer experiences programming were more kind of confused about the tool. They either thought it wasn't trustworthy or they weren't able to as effectively sort of interpret or use the output that it's giving them. You know, I think the slicing is actually pretty good overall. Like, there were more people who said, I felt it just sort of faded into the background. And within like a matter of minutes, people were able to kind of debug with this in mind, rather than have to consciously think about the fact they're using a program slicer. So that I consider a major success. But it is true, especially for these trickier cases, like if we wanted people to say, notice that something is outside the relevance region, that's a more complicated inference that I would expect to take training with the tool and with programming in general to realize might be important for, say, debugging that task.
Yeah, just a it definitely seems like it's a hypothesis accelerator.
Yes.
And often the hard part is having the knowledge to generate hypotheses in the ballpark.
Right.
And so that's sort of what I'm interested in, like maybe going forward, can you consider how to help people propose hypotheses with this sort of
Yeah. There is a whole body of work on what's called fault localization, which is exactly this task of, given there's a bug, suggest a line, like, it's a little bit different. It's suggest a set of code that might contain a bug.
Which is like what everybody in office hours knows that every student comes in. Can't do very well.
Yeah. Yeah, so I agree. I think this is totally complementary with that work. Although I've not personally seen I think the nice thing about slicing is you can see it much more like a tool like jump to definition. It's a tool that can kind of just work in a somewhat reliable way since it has clear semantics that we can establish in most cases, whereas fault localization is much more of a statistical kind of thing. It like may work, it may not work, there can be tons of false positives, and I think that's part of the reason why those tools haven't seen as much adoption. Let's try again. Is there any questions from the Zoom?
Yes. Can you hear me?
Yeah, we can hear you, Sridhar. Go ahead.
I think you can.
Should we try Sridhar for the closed session?
Oh yeah.
Now I can wait till the closed session. I don't want to. The echo is going to be bad.
That's fine. Just go ahead and ask your question.
Well, okay. Let me start by asking. You started by telling us about a tracing task and measuring cognitive load in the tracing task, and
Yeah.
I wondered about the authenticity of that measurement. You know, it's like I would never measure without, if I were asked to do that tracing, I would have done it with a scratch pad, right? Which is the natural thing that any human being would have done. So
Yeah.
it feels like you created an extremely artificial task. And then you told me that that task without the natural support I would have is really bad. And I was trying to think, I mean, I know tracing is a common thing that people use in the computing education literature, but I've never quite believed in it even there. So I was hoping you could convince me that this is a thing I should care about, especially the way you set it up.
Yeah. Okay, 2 thoughts. So first, I think that it's true that if I gave you that specific task, you would sit down with a notepad and compute it, right? But I think the reason why it's meaningful to investigate it as a purely mental task is because in general, when you are reading a piece of code, certainly it is my experience that more often than not, you may not have the ability to add annotations to that program. Like let's say you're reading a GitHub PR or something like that. And the only way you can annotate it is by like leaving a public comment to the person you're talking to. Or, of course, you're reading code and maybe you can like leave some comments here and there, but now you're cluttering up your program. Like there are lots of cases where you're reading code and you don't have sort of the affordances to externalize information that you're generating about that program. And so holding state in your head, which is the ultimate thing that's being measured, I think is still relevant. We just had to sort of artificially enforce it here, even though, of course, you would ideally like to do this without, like, of course, yeah, you would like to externalize this information, but I think in many cases that's not possible, right, depending on the task.
I think that's actually a really good response. It's even better than I was expecting. And I just want to call out Joshua. Joshua has a comment in Zoom. Joshua Nelson says, I'm surprised to hear that from Sharm. I don't think I've used pencil and paper tracer program in several years. But I think what this is actually pointing out to me is, and this is like a future research thing, right, is why don't we? Like, why do I have to pull out a piece of paper to write this down, and which I'm not going to do? Why aren't our IDEs and language tools giving us the ability to do that in a more direct way? Is to me the real conclusion of this conversation. But
right, I totally agree. I think clearly externalization of information, not holding it in your head, is the ultimate like design outcome of the study. And the point is, there's just two ways to do this. Either you have a tool that automatically does some of this information analysis and visualization for you, like the slicer or the gold pane, or you have some kind of like interface yourself. And I think these are complementary. Yeah.
Okay, the trolls have shown up on chat. So okay, so I have another question. So just going back to your tracing task, you talked about your linear versus on-demand behaviors, and I couldn't help but notice that the pictures you drew are very similar to the pictures I imagine when looking at the literature on forward versus backward planning. This is going back to stuff that Herb Simon started, and then Riss did, and so on. I'm wondering if it's just like just forward, backward. There's nothing deeper there, or is it just coincidence? Is there any connection that you can think of? Because I know you know some of that literature too, so you might have spotted connections there.
Yeah, I think there are probably maybe loose connections. I think the line of reasoning is a little bit different, right? For me, the most salient thing is, I don't actually know why people pick each strategy. I think that's an interesting question, which probably is relevant here of like people. So in practice, by the way, what we found is people did it at a preference. Like on balance, people would choose linear or on-demand tracing and not switch. So clearly people like felt that it was good to do one or the other, and it was about 50-50. Like there was not a significant majority preference for one of these strategies. So, like my hypothesis would be like, some people see the question, they see what they're supposed to compute, and so they just say, I'm going to start with the thing I need to compute. Or some people who say, I see a program, I have to read this program before I answer the question. Top to bottom. I don't know if that's true, but I suspect it's like sort of more succinctly, like Occam's razor, just answered by one of those questions. But it's a good point. I think this is something also to investigate. It's like, tracing is very low level, but like as you get closer to general program comprehension, right, you're talking about like understanding why the program is written the way it is, then I think you get much more into sort of like schemata and like forward and backward planning.
Right. Well, in particular, the thing that Simon was trying to investigate, this was, on the heels of his like chess studies, right? He was trying to see whether novice versus expert programmers do different things. And I do wonder, like what you just said, right? Like I could easily imagine that a novice programmer is, I'm given a program, I should read it. And the more expert programmer is, okay, I see what you're trying to get me to do. What's the most efficient way I can do that? Maybe I should start at the back and work my way, start at the end and work my way back or something. Okay, I'm going to stop now because I'm sure it's getting irritating to have like this booming voice and echo and stuff. So I'll stop now and I can ask you more questions later, which I do have. So.
Yeah, that sounds good. David, do you have a question?
Yeah. So it seems like you're talking. It seems like when I look at the example, it's a lot of debugging sort of a known unknown. So I know I have a lot of code in this file and something's wrong there.
Yeah.
But a lot of my concerns around dealing with a large code base are the unknown unknowns of there are 50,000 other files. What went wrong? Wait, like what else? Can you sort of expand on maybe in the future how you might expand flow street to deal with sort of everything else, in the program that isn't in my file?
Right. Well, in some sense, that is, I would say, exactly Damon's question about fault localization. That the goal of that is you have some big, huge mass of code, and you need to find like the entry points into this, the likely at least surface cause, if not root cause of the bug. And so tools that can point and say like, this line of panics are a good example of this, right? You get a panic, it says these are the lines of code where the panic occurred, and so in that case, you just jump to that line of code and you sort of start debugging from there, right? Trickier bugs may not be so easy, but I think yeah, there's sort of this disjoint category of fault localization techniques, whether that's automated or that a programmer adopts, that are needed for that initial step. And then slicing is useful kind of past that. Once you have identified a place where a bug could be, then let's start figuring out only what code is relevant to that bug, for instance. Yeah.
Yeah, I'm curious whether you think regular access to a slicer will affect program design. In particular, I'm curious whether you looked at any of the 6% of instances where the type-based analysis was less precise than the code analysis. And I wonder if any of those instances were sort of instances of poor design or code smells or that sort of thing.
Yeah, we've talked about this, how you could use information flow analysis like as a linter or as some kind of code authoring tool. In the case of the empirical study, I think most of those were just imprecision arising from our approximations. Like, I didn't look at the code and obviously it was like, well, because our slicer is imprecise, this code is poorly structured. But, you know, I mentioned the decomposition prototype. And that I think is something that's a little more interesting, where if you have some big spaghetti code, then you can sort of zoom out and say, well, what's like the rough structure of this code? What are the rough components of, oh, sorry, I should share this so people can see what I'm talking about. You know, what are the rough components of what's being visualized here? And there we go. And so, you know, you can imagine here, you run this and maybe you tweak your components and then you click a button that's like refactor and puts this into 4 different functions, for instance. And I was talking with actually several people in the study about this because they mirrored that same thought of, you know, the biggest issue I have is with messy code. You have lots of developers working on a code base and then they leave and nobody remembers anything about the original design of the code. And so things just get added in ad hoc and now it's scattered around everywhere. And so it would be really nice if you had something that truly understood the dependencies between these code so as to, like graph is almost, you know, force directed layout your code to make that graph prettier. I think that's a very interesting direction. There are a lot of logistical issues about like actually source level rewriting of the code that we haven't dealt with that are interesting to get into, but it's definitely, yeah, something we're other questions on the Zoom?
Yes, can I ask a question? Do you hear me?
Yes, we can hear you, please.
So I was wondering, you said that this analysis is sound, and I was interested in how you handled the interior mutability in the soundness proof.
Yeah, so the big asterisk on this tool is it is sound for safe rust, right? The subset of rust in which we formalize this tool, Oxide, describes the kind of constructively ownership safe, as in ownership safe with rules where every line of code can be constructively proved or internally consistently proved to be ownership safe. But for those of you who don't know, there's this concept in general Rust of interior mutability, where you can have code that is not possible to prove that it's ownership safe. So you implement it with what's called unsafe mechanisms, and you promise, I did this correctly, and at runtime, it will be ownership safe. I promise, you have to believe me. That's essentially the way that it works. And so there's no way for our analysis to deal with that. Like once you go beyond ownership, or at least like ownership types, and you've given up on that, this code will be unsound. It will miss information flows arising from the usage of interior mutability. But I think the kind of saving grace here is that, at least both in my experience and from our experiments, like the majority of Rust code does not use unsafe. And the majority of Rust code also is just written in a pretty standard way, not using like RC ref style around every data structure. So I think this is, it's useful, but an important direction here is, can a tool communicate to the user when you are reading code which is within this boundary of like, I may not be able to give you a fully correct answer because you're using these dangerous features. I think that's an important direction to go, going back to trust, to establish trust that participants could have with the tool. Yeah, great question. In the back. Okay.
It kind of like a follow-up on that. Do you think there is value though in like having the ability to have a tool that says, okay, this is a print function. Usually print functions don't modify a variable, and so we'll just say like with an understanding that this isn't a fail-safe thing, is it still worthwhile saying this will work on most programs and sort of having that extension? Or is it something that should be like ultimately reliable because of the implications? If it doesn't work, someone could completely not be able to find something.
Right. I mean, my sense is, like the borrow checker in Rust is exactly in the first case of what you're describing. Like it is good, it's safe to use, it will protect you from memory safety until you use unsafe features. And so there's this kind of social contract in writing Rust code that everything is safe until you decide to, do everything on your own or stray into the unsafe features, at which point you need to be much more careful, and there have to be much clearer constraints on what you do, and there should be some kind of argument as to why what you're doing is safe, as opposed to just believing the Rust compiler. And similarly here, I think the slicing tool is useful. It is useful for plenty of Rust code that is written in this way, but likewise, it should just be clearly telegraphed to the user where that boundary exists.
So maybe as a follow-up on this, a more pragmatic question on generalizing this to other languages. Right. So you have ownership types, and it seems like people write those in Rust. Let's say we're using Python. And where do you see the design space of people needing to insert annotations versus use of like the analysis suffering from a lack of Soundness?
It's funny because I have some friends who are trying to implement a program slicer based on these on information, or like with clear relationships to information flow. They're trying to implement a program slicer commercially for Jupyter notebooks, and I have so much sympathy for them. I mean, it just seems like an impossible problem, and it's just a huge bag of heuristics. And the thing is, at the end of the day, I bet if they carve out enough of Python, a subset of Python that like data scientists use, and they add enough stubs for like every pandas function, then they'll have something that works for most people in most cases, right? So I don't think it's impossible. And like in their case, they focus more on dynamic analysis. So they accept we have to dynamically analyze this, and we just do as much as we can running this. And there they have sort of the like code execution problem. How do I know I've hit every branch? So when I pull out this code, it's actually going to run as I expect in production or something like that. So yeah, I think it's still possible, and I do think there are interesting ideas to pull out from this of like what kinds of, for instance, what sort of approximations are reasonable versus aren't reasonable, right? For one thing we highlight in the study that I don't show is if you analyzed Rust, but you didn't know about the mutability of these references, like if you ignored it and said any reference could be mutated, for instance, like in C, then the size of your slices goes up by like 50%. They're much larger. And so those features are very important in this case to getting reasonable precision, I think. So it's not clear how you would port that to Python, where of course anything can be mutated ever all the time by anyone. But there's probably still at least some cross-pollination. But partly, it comes down to those 4 criteria just aren't reasonable for, like, while I do think in a sense they define a practical tool, like you literally can drop in Flowstream and it will just work in your code base. It's not practical. It's impossibly practical for stuff like Python. Yeah. Maybe, I don't know, we should probably end soon. So
Yeah,
we
maybe we have time for one more question.
All right, Zoom folks, you get one last question. Does anybody have a hand up and want to say something?
Sure, I could ask you a question unless somebody else wants to. Is anyone else on Zoom?
Well, hold on.
Yeah.
I'll get into the private session.
Not sure. Yeah.
Okay, good. Okay, good. Somebody else. Thank you.
Joshua has his hand raised.
All right, yeah, Josh. You're muted, Josh. Oh, yeah. How hard would it be to extend this to interior mutability? It would. So I think there's a version of this where you sort of just say you just make far more conservative approximations. Like, well, okay. On one hand, I think it is impossible in a purely intra-procedural way. You cannot maintain modularity while ignoring the source code of interior mutability. So you sort of have 2 options. Either A, you have to do a more inter-procedural analysis involving functions that contain interior mutability, or B, you have to annotate the interior mutably functions that use interior mutability to provide information specifically for the information flow analysis, which of course I don't think would happen in practice because that's a huge amount of effort, and not every tool wants to annotate itself to work with the flow tree. So probably the whole program analysis is the only thing that makes sense. And there, I think the trick is, can you like selectively determine at what times you need to be whole program versus interprocedural, as opposed to just always analyzing the whole program, which can get arbitrarily slow.
Yeah, can you hear me okay? Is the audio working?
Yep, I can hear you.
Awesome. I think this would actually be a little easier than whole program analysis because you know which types have interior mutability and which don't. And so you only need to track functions on that take a type with interior mutability and not every single function in the program. But I definitely see how it's harder than if you had it available like at the type level.
Yeah, that's a good point. I think that would be interesting to look at. It's sort of like a taint analysis of, we know these things are tainted by interior mutability, and therefore we just apply a more conservative analysis to them. That could be something to explore. Yeah.
Awesome, thank you.
Great questions. We'll wrap it up here. Thank you all for attending. And